speaker is François, and he will present us some quantum distributed algorithms.
Okay, thank you. So we consider the following question. So does quantum help for distributed computing? And we know some positive answers in some models of distributed computing, for example, for anonymous networks, faulty networks, or for quantum multi-party communication complexity. But in the classical distributed computing community, two other models are extremely popular recently, the CONGEST model and the local model. And I will explain these two models in the next slides. And these two models have been studied in the quantum setting in 2009, 2014, but unfortunately the results were mostly negative. It has been shown that it's impossible to obtain a speed up using quantum computation in this model for many important problems, like computing the shortest passes or computing minimum spanning trees. And, but recent work has shown that for other problems, you can obtain speedups. And today I would like to talk about these results. So let me describe the model, CONGEST model and local model in the classical setting first. So it's really a basic, one of the most basic settings in distributed computing. Everything is non-faulty, non-anonymous, and synchronous. So you have a network of n nodes represented as a network, as a graph like this, and all nodes have distinct identifiers. And each node initially knows only the IDs of its neighbors. And we assume that they know also the total number of nodes. So for example, node 4 only knows that it is connected to 1, 3, and 6, but does not know anything else about the topology of the graph. And communication is synchronous and between neighbor, adjacent nodes. So at each round, one message is sent through each edge in each direction. So for example, at round 1, all the nodes exchange one message. Then there is local computation. We don't care about the cost. It can be exponential time. We don't care. And then another round of communication, then local computation, and then again communication, and so on. And we care about the round complexes, number of rounds needed to do the computation. And then there is an important parameter, which is the size of the message. And here comes the two models. In the CONGEST model, we assume that each message is short, concretely log n bits. Why log n? Because it's exactly what you need in order to encode one ID. While in the local model, there is no restriction on the size of each message. Okay? And both models are very interesting and well studied in the classical setting. For example, the local model corresponds to a situation where communication is very fast and cheap. And what you care is really the number of rounds needed to reach the conclusion of your computation. Okay, and now the quantum settings, very easy. Now we can send quantum bits instead of classical bits. Okay? So this means that each node is a quantum processor and message quantum bits, and so the edge corresponds to quantum channels. Okay, and we are again interested in the round complexity. And we have the two models, the quantum CONGEST model with small quantum messages, and the local model with no restriction on the size of each message. So is there any questions on the model? Is it clear? Okay, so let's first describe this advantage, first advantage, quantum advantage in the CONGEST model. It's a recent work with Frederick, and we have shown that the diameter of the network can be computed in square root n rounds in the quantum setting, while classically you need n rounds. So it gives you a quadratic gap when the diameter is constant. Okay? So what is the diameter? So here we consider only undirected and unweighted graphs. The diameter of the graph is defined as a maximum distance between two nodes. So for example, in this graph, the diameter is 4 because the two most remote nodes are F and G. And 1, 2, 3, 4 hops. And the diameter can be rewritten as the maximum eccentricity. Okay. The maximum eccentricity, where the eccentricity of a node is defined as the maximum distance between this node and another node of the graph. We will use this characterization later. Okay. So now I will define a basic but very fundamental classical distributed algorithm for computing distances. So assume that you want to compute the distance, say, from node 1. This can be done by using the breadth-first search algorithm. It's a very simple algorithm. Okay? So first, the source of node 1 sends a message to all its neighbors. Then, all the nodes that receive a message know that they are at distance 1, of course. At the second round, all the nodes at distance 1 send a message to their neighbor. Okay? And at the end of round 2, all the nodes that received a message for the first time at round 2 know that they are at distance 2. So they update their distance. And we continue like this until everybody knows its distance. And of course, the complexity is precisely the eccentricity of the source, okay? Which is upper bounded by d, because d, the diameter, is the maximum eccentricity. Okay? To summarize, this algorithm enables you, for one fixed node u, to compute all the distance from u. And it's... It's a good question. There are several things. I mean, you can compute an upper bound of the diameter very easily and stop when you reach that. And you can propagate back the information to tell everybody that you can stop. It's a good question, but it's not very important for today's talk. Okay? And then, so you can propagate in d rounds, and if you propagate back the information, then you can compute the maximum of this distance as the eccentricity. The cost will be a big O of t. But the point is that computing the diameter, that is the maximum eccentricity, is much more complicated. You need a linear number of rounds, even if the diameter is constant. It's a little bit surprising. It has been shown fairly recently. And we have shown that actually you can do better in the quantum settings. So here is the detail. The computation of the diameter, classically, as I said, it's n. You have an upper bound and a lower bound of n. And quantumly, you have an upper bound of square root nd. So in particular, when d is sublinear, the complexity is sublinear here. And when d is constant, this gives you a square root n, which is quadratically faster than the classical bound. Okay. And we also have some lower bounds. This one, square root n plus d, and another one, which is tight, but it's conditional, under the condition that it's all only for quantum algorithms that use only few memory, a polylog memory. And all algorithms actually use only polylog memory. And I should mention that all these bound and lower bound, the classical and the quantum ones, are obtained by proving reduction from the two-party communication complexity of the disjointness function. And I should also mention that the very recent result by Frederick and Ashwin actually improved this unconditional lower bound to this thing. Okay, and from now I would like to describe the upper bound. Okay, so we want to compute the diameter. Let's consider the decision version of this problem. Okay? I give you an integer d, and I ask you if the diameter is larger than d or not. Of course, if you can solve this version, you can solve the original version. So we have to decide if there exists a vertex u such that the eccentricity of u is larger than d. So it's a search problem. So the intuition is let's try to use Grover search. So concretely, you consider this function f defined on the set of vertices with value 1 if the eccentricity is larger than d, and you want to find a u such that fu is equal to 1. And we know by Grover search that this can be done using square root n calls to an oracle evaluating the function f. Okay. And we all know the details of Grover algorithm, so you apply the Grover operator square root n time and you measure. And the Grover operator apply an oracle, Adamar gates, phase gate, and Adamar gates. And the point here is that the only point of Grover circuit here that depends on the function f is a call to the oracle. All the other things are independent of the function. Okay? So now our strategy is as follows. We take one arbitrary node of the network, a leader, say the node with the smallest ID, and we ask the leader to implement this circuit, the whole circuit. Okay? So now the leader can do this locally because it's independent on the network. It can do this and this also locally, but it cannot implement the oracle purely locally because the oracle depends on the function f, and f is essentially the eccentricity, depend on the eccentricity, which depends on the whole network. So the idea is that any time the leader will need to implement one call to the oracle, the leader will communicate with the other nodes to simulate this oracle. So the total complexity will be square root n, the number of repetitions, times the cost, the number of rounds needed to implement one call to this oracle. And now I will explain how to implement this efficiently, the call to the oracle. Okay? So the oracle should compute the function f. So this means it should compute the eccentricity, and of course in superposition. And I will explain how to do it on this example, okay? With the leader being the node A. So initially, the node A has this state. I want to create this. So the first step is what I call broadcast this state. So what do I mean? So first, the node A introduce one register here with a 0, initially at 0. And the node A apply one C naught. Copy the information of U here. And the node A sends the second register to C. So it sends the register to the next node here. Now, the node C will introduce 3 registers, perform C naught operation, and distribute its 3 registers to its children, B, C, and D. And you continue like this. Okay? Each time you introduce a register, you apply C naughts, and you distribute to your children. Okay? It's what I call broadcast the state. Okay? At the end, you obtain this. It costs the eccentricity of A exactly, which is a pair bounded by T. Okay, so now the next step. The nodes implement the classical protocol for computing the eccentricity. I mentioned a few minutes ago that this can be done in D rounds, computing the eccentricity of one vertex. The nodes apply this protocol, and we get the eccentricity here. So this part is completely trivial or very subtle, depending on how you think about it. You can think of this. You have a classical protocol. You can think of the classical protocol as a circuit, classical circuit. And then you can consider a reversible version of it, and then a quantum version of it. And this quantum version of it will do exactly this. We'll pre-compute the eccentricity in superposition, so we will be able to do it in exactly the same complexity D rounds. And then finally, you revert the step 1, which erased all this intermediate register, and you get exactly what you wanted. Okay, so total complexity is a big O of T. Essentially because you can compute one eccentricity classically in a big O of T. Yes?
What happens if a node receives more than one register? Just throw away the other?
They won't really they don't throw away the other, no. So I mean, you have the same issue will arise in a classical protocol, okay? A classical protocol will receive many messages and will do something. And this something will, at the end, enable to get the eccentricity. And then we do a mechanical conversion of this classical protocol into a quantum protocol. So we don't really have to think about all these issues. They are dealt by a classical protocol for computing the eccentricity. Okay? But you have to think carefully about what a classical protocol means. Okay, so to summarize, so we have our quantum search that enables you to solve this problem using square root n calls to a black box, and our strategy to ask a leader to simulate that. and the leader can do everything except the call for the oracle, and each call for the oracle is implemented by using the quantum version of the classical algorithm for computing the eccentricity. So the overall complexity is square root n times large D. Okay? And with further work, this can be reduced to square root nd with a D inside the root. And maybe I can say one word about that. This is actually because we have a stronger result. Here we used D rounds to compute one eccentricity. But there is a stronger result that says that in D rounds you can compute D eccentricities simultaneously. So this means that you can do the Grover search over groups of D vertices, which reduces the size of your search space. And it puts the D inside the complexity, inside the square root in the complexity. Okay, so this gives you this upper bound. We have this lower bound. The, of course, open problem is to prove an unconditional lower bound, matching, tight. So we have this bound, which is better than this one, but still not tight. Another thing is that our upper bound is obtained by showing how to implement quantum search in a distributed setting. It's a very generic technique, so it should have a lot of applications. Okay? And for example, recently we found 2 other applications to design quantum distributed algorithm for the old pair shortest path problem and also triangle finding. And they are not actually completely trivial because for old pair shortest path, for example, you need to implement simultaneously n-square quantum distributed search. In particular, you need to implement simultaneously n-square checking procedures. So you have to be extremely careful about how to balance the load of your message in order to avoid congestion. So it requires a lot of subtle techniques from classical distributed computing to do that. Okay. So this was the first part of the talk about the CONGEST model. We have shown that quantum can be useful for some problems. Now, what about the local model? So the local model is different because there is no restriction on the size of each message. So you want to compare an unbounded amount of quantum communication and an unbounded amount of classical communication. It looks a little bit more challenging. In prior work, there was a computational problem that can be solved in 1 round in the quantum local model, but requires 2 rounds classically. And recently, we have shown that actually you can have a much larger gap. There is a computational problem that can be solved in 2 rounds quantumly, but requires a linear number of rounds in the classical setting. Okay. And I will explain briefly this problem. It's based on a construction by Barrett et al. Dating back to 2009, and I think many of you know it because it was also used in the recent result on quantum shallow circuits. This is this thing. You can think as a ring or as a triangle. So size n a multiple of 3. So you're seeing as a triangle with 3 sides, each of length n over 3. Each corner gets a bit. Okay? We have 3 corners. They get a bit as an input, b1, b2, b3. And each node will output 1 bit. This will be the output of the problem. And now consider the following process. The nodes prepare the graph state corresponding to the whole triangle. And then all the nodes which are not in the corner measure their qubit of the graph state in the x basis. So they get 1 bit, and they output that bit. So now each corner node measures its qubit in the x basis if the corresponding input bit is 0. Otherwise, measure it in the y qubit, in the y basis. This gives you a bit, and this bit is output. Okay? We know how to implement this process in a shallow quantum circuit. It's not difficult to show that in the setting we consider distributed computation, this can be done in 2 rounds. Essentially, each node has only to communicate with its neighbors and get back some information. So 2 rounds for the first step, preparing the whole graph state, and you don't need any communication for measuring and doing the output. So you can do it in 2 rounds in the quantum setting. But we can show that classically, any classical algorithm that samples from the same distribution must use at least n over 6 rounds. The proof is from the paper by Barrett et al. It's fairly easy. So if you have less than n over 6 rounds, essentially you cannot gather at the same point two input bits. This means that each output can only be an affine function of the 3 input bits, and you can show it's not enough to sample from this distribution. Okay, so this gives you 2 rounds quantumly and n over 6 round classically. Yes?
What is the input bit in step 3?
Input bits are B1, B2, B3. Okay, so for example, this node is a corner. So you look at its input, and if the B2 is a 0, it measures in the x basis, and if it is a 1, it measures in the y basis. Okay. So the only exception is the corners that follow a different rule, depending on what they receive as input. Okay, so we got this is the result I mentioned before. So the computational problem is simulate the outcome distribution of a measurement of a graph state corresponding to the ring. A few remarks. Actually, our quantum algorithm, so the part of creating the graph state, actually requires, it's 2 rounds, but only very short messages, 1 qubit per message. You only need to send 1 qubit and receive back 1 qubit. So what we get is actually a stronger statement, a separation between quantum congest and classical local. That's the first remark. Second remark is that you can show similar separation for a relation. So if you don't like distribution, you can have also separation for a relation. And the third remark, which is more interesting, is that we can also get a similar separation for a sampling problem without any input. In the previous version, we have 3 input B1, B2, B3. You can get a version without input by taking B1, B2, B3 uniformly at random. And it's interesting because we don't know how to prove the same result for shallow circuits. Okay. So the conclusion, we now know that the quantum distributed algorithm can be faster than classical distributed for several problems in both the CONGEST model and the local model, which are very important model in distributed computing. And a few research directions. So first, the main one maybe to construct other quantum distributed algorithm for important problem. This is actually, I think, very interesting because this poses a lot of new algorithmic challenges because we really have to focus on the round complexity. It's a little bit different from optimizing the time complexity, the query complexity, or the communication complexity, things that we have done in the past 20 years. It's a fairly different thing. Second thing, develop new lower bound techniques for quantum distributed algorithm. As I briefly mentioned, for the CONGEST model, you can obtain some bounds using two-party communication complexity, two-party quantum communication complexity. But for the local model, we don't know any non-trivial lower bound. And the third thing, so we considered here the CONGEST model, the local model, but there are many other models in distributed computing, so we can consider quantum version of these other models and check if they are more powerful than the classical version. So for example, this week, we uploaded a new result that study distributed version of interactive proofs, and more precisely quantum version. And we show that the quantum version can be exponentially better than the classical version. Okay, that's all. Thank you.
Questions? Do you think that some of these ideas can be generalized to a more paranoid setting where, like, you don't trust all the partners?
Yes, of course. I don't know. I don't know the answer, but it's an important part of research on classical distributed computing to consider faulty cases or cases where there are bad guys, adversaries, the cases where there are noise. So you can ask what is the power of quantum in these settings. I haven't really considered that yet, but it's a good research direction.
Is your triangle setting robust to error? The last one.
I don't think so, because if you kill 1 qubit, you lose all the quantum correlation. So it's probably just yes, this version. No.
So you mentioned an improvement for triangle finding, right?
Yes.
What exactly?
So quantum, classically, you know that the best upper bound is n to the 1/3 rounds. So it's a classical. And a quantum that we get is n to the 1/4. So it's an improvement over the classical case.
I think you showed a conditional lower bound in the CONGEST model.
Yes.
What was the assumption?
The assumption is that the lower bound holds for any quantum algorithm that use only a small amount of quantum memory. Polylog qubits of quantum memory. And our quantum algorithm does use exactly this small amount of quantum memory. It's tight at least for all kinds of quantum algorithms, but not necessarily for other kinds of quantum algorithms.
No more questions? So thanks again.